Hello, Fazin, Isjay, and welcome to the next installment of the Tribal Alliance for Pollinators 2020 webinar series. Today's webinar brings us right back to the beginning of where Tribal Alliance for Pollinators began, with Dr. Chip Taylor and the declining monarch population. Many of you on this call have been with this project since it started way back in 2014, but it's worth taking just a brief moment to acknowledge how far we've come and how much of it we owe to Dr. Taylor for making it possible. What began as 7 tribes in Oklahoma learning how to restore monarch habitat under the tutelage of Dr. Taylor grew into an organization called Tribal Environmental Action for Monarchs, or TEAM. We're big on acronyms around here. That then grew into a much larger organization that we have today, Tribal Alliance for Pollinators, or TAP. The team and TAP have gone from a tiny grassroots project to the point where now we have worked with representatives from over 40 tribes from throughout Oklahoma and across the United States on restoring habitat for monarch butterflies and other pollinators. Today, Dr. Taylor will be discussing a significant threat to the monarchs that hasn't had much mainstream media attention yet and needs to be more widely known. We're grateful to him for taking the time to present the science to us today and for all the support that he has generously provided to the team and the TAP for the last 7 years. In addition to being co-founder and co-director of Team and TAP, Dr. Taylor is better known as the founder and director of Monarch Watch at the University of Kansas. Besides being one of the top experts in the world on monarch butterflies, he is also a world-renowned expert on Africanized honeybees and a retired professor emeritus of ecology and evolutionary biology at the University of Kansas. Before I turn it over to Chip, I have a couple of quick announcements. Our next webinar in the series will be on December 15th. It will be about the tribal adaptation menu and building climate resilience through indigenous knowledge. We've also set the dates for the 2021 TAP conference, and it will be a very big multi-day event on September 21st through September 24th, 2021 at the Uchi Butterfly Farm. We do have a lot of travel scholarship funds available due to all the events being canceled this year, and we're hoping to get participation from all the tribes in Oklahoma and as many tribes from across the country as possible. Our beautiful new website, tribalallianceforpollinators.com, will have details about the conference posted soon, and it also has the registration link for the upcoming webinar. We will take all questions today at the end of the webinar, and you can type them into the question box on your webinar dashboard at any point, and then when we get done, then we will answer all the questions. And with that, I will turn it over to Chip.
Hello, everybody. Good afternoon. We're having a beautiful day here in Kansas, and I hope you are wherever you are. And I'm glad you're with us today. I'm going to talk about climate change, monarchs, pollinators, insects, and us, of course, because we're affected by all of those things. We're affected by a lot of climate things, and I'm going to try to lead you through this. Basically, I'm going to present you with maybe the cliff notes of maybe a 3-semester course in climatology. We're going to try to cover a lot of ground. Don't be scared. You're going to be looking at a bunch of data here and there. And you have to know data, and you have to look at data if you're going to understand what's going on with respect to climate change. So we'll be doing a little data diving in order to kind of understand what has been happening and what is likely to be happening in the future. All right. Let's go to the subject matter. While we'll be talking about monarch butterflies, we're actually talking about virtually all pollinators. Monarchs are vulnerable to climate change, but so are most insects in one way or the other. Another group that is extremely vulnerable, more vulnerable than monarchs are to climate change, are the bumblebees. Bumblebees have a low reproductive rate. They survive from year to year on the basis of the number of queens that go from one fall to the next spring. And if that number is diminished significantly by not having enough resources in a particular summer, so that you don't have enough queens going into the winter, or if a lot of queens die during the winter, then the bumblebee populations go down. Most people aren't aware of how vulnerable that group is, and we're seeing a lot of people doing a lot of hair pulling about what's going on with bumblebees, and they're under threat for a lot of reasons, including climate change, but also introduced parasites and pathogens. All right, so a number of other things. So let's get to the kind of big picture first, and then we'll kind of dissect that big picture and see if we can get down to the nitty-gritty in terms of what has been happening. What you see here is a record of world temperatures, land and ocean, on an annual basis, January through December, and we're looking at the temperature anomalies from 1880 to 2019. And you can see that right up through the late 30s, I was born in 1937. You can see where that, it was all my fault, I guess. It's about 37 things began to change. Now it got warmer after that in the 40s, a few dips in the 50s, and a few dips even in the 70s. But generally, we've seen since the 40s, we've seen an increase in world global temperatures, and it's been a really significant increase, and it's not going down again. It's very, very clear that we're not going to see those blue bars again in the future. Things have really changed, and we'll talk about why those things have changed as we go along here. All right, so here's the next thing we can look at, and because this is really relevant to us, we can look at the Northern Hemisphere, and we look at only at the land, not just the land and the ocean. And this is interesting because I can point out one little anomaly on this particular graph, and that is this little blue bar that's way over here to the right, the last blue bar on this graph. If you were in my classroom right now, I would be hectoring you and harassing you about why that little blue bar is there, because you should know why that little blue bar is there, because you have heard me talk about this before. And if they don't remember, I'm going to remind them and give them a little hard time, because everybody should know that one of the things that really changes the climate on a short-term basis, but can do so significantly for a number of years, is a volcano. And that little blue bar represents the volcano for Mount Pinatubo, that Mount Pinatubo explosion that occurred in 1992, changed the temperature of the planet for about a year and a half because it put up a dust veil. A dust veil is the dust from a volcano that gets up there about 35, 40, 45,000 feet. A lot of volcanoes don't put up dust that far, but if a dust gets up that far, it creates a blanket by which a lot of incoming radiation cannot penetrate, and that has a cooling effect on the climate. There's lots of talk about creating an artificial dust veil so that we will cool the climate. I don't think that's a very good idea, but people talk about these things anyway. That would be a massive undertaking. But in any case, dust veils are important. They're not a frequent aspect of what's going on here, but there is a little historical tidbit that I can throw out to you that you can remember and tease people about. Who was the first person who figured out that volcanoes actually change the climate? I'll bet you don't know. Anybody? Anybody got this one? Yeah, it was that famous climatologist, Ben Franklin, in Paris. When he was in Paris for a couple of years, he experienced a really cold summer, and he figured out that that cold summer had to do with a volcano. He got the idea right. He got the volcano wrong. Turned out that a volcano had occurred eruption had occurred on Iceland, and that had changed the climate of Northern Europe for that particular year. Didn't change the climate everywhere, but it changed the climate for that particular year, and he figured it out. So you can tell everybody that Ben Franklin was really a visionary in a lot of different ways, but one of the things he figured out that nobody else had put together was that volcanoes can change the climate. All right, let's go on here. I'm having a little hard time with this cursor here. All right, let's take a look at past climates and events and try to understand what's going on now based on what happened in the past. So we had the last glacial maximum about 600,000 years ago, and the last glacial period about 11,700 years ago before present. That means that we have a glacier that it dipped down in North America, dipped down in Europe as well. And we had a period which is called the Little Ice Age, and there's a nice book on the Little Ice Age if you care to read it. And it talks about all the events that occurred in that 550-year period from 1300 to 1850. There were a lot of volcanic events, there were a lot of shifting pressures, there were droughts, And amazingly, during that period, glaciers actually grew to the point where they actually swallowed villages in Switzerland. It was pretty amazing and quite different from what we're experiencing in the last 170 years. Well, let's get back to major eruptions. Tambora was a fantastic eruption that occurred in Indonesia in 1816, and it had an amazing effect on the development of Eastern North America because it created a year without a summer. It was snowing in July in New England. Crops totally failed, and that resulted in a mass exodus of people out of New England into the Ohio River Valley because they figured that they could never survive year after year of conditions like 1816. Well, it turned out that that was a fluke year and it was caused by Tambora, but they hadn't figured that out yet. The other one, the other big and last big explosion prior to Mount Pinatubo was Krakatoa in 1883. And Krakatoa again created a tremendous dust veil, and it changed the images of the evening sky all over the world. And it was said to have inspired The Scream by Edvard Munch in 1893. But there are disputes about whether Edvard Munch actually was influenced by that, the skies caused by the explosion of Krakatoa. Nevertheless, once people started to think about how artists were depicting skies, they went back historically and looked at how artists were depicting skies, particularly late afternoon and evening skies in the historical record. And they could figure out, they actually did figure out that many artists were depicting skies that represented the dust veils of various volcanoes that had occurred historically, which is another interesting thing. Volcanoes changing art as well. All right. So what's actually happened since 1850 at the end of the Little Ice Age? What's happened at 1850 was not much. 1850 was a period where it started to warm up a little bit, but things had not really changed. And they hadn't really changed because we hadn't really shifted to new sources of energy. Prior to 1850, we had been using a little bit of peat, tiny bit of coal, and we had been using a lot of wood. And so our energy sources were very limited. Water power was fairly limited. And we really hadn't discovered power. But in the 1870s, we really began to dig into fossil fuels. And you can see that suddenly in 1870, where my cursor is, if you can see my cursor, things began to increase. And what increased was, you can look at this total carbon emissions over here, this kind of deep maroon sort of line. And then you can look at the contributions of different things like gas fuel, liquid fuel, solid fuel, and cement production and gas flaring and so on and so forth. But the net effect of that was that, that things really changed. But look what really changed. What thing that changed in a massive sort of way as a result of this was the human population. Human population in 1850 was 1.2 billion. 1.2 billion. And look where it is now, 7.7 billion. So what the age of energy, I call it the age of energy. It's this age of adoption of fossil fuels to provide energy, which transformed virtually every industry, pharmaceuticals, development of plastics. It's just an amazing number of things that have come about because of the use of fossil fuels. There's no question that this has been the dynamic that has fueled population growth because we have reduced death rates, we've increased longevity overall, and it is largely due to the fact that we've made a lot of advances on the basis of being able to harness a lot of energy. And now the question is, what is the cost of that? And the cost of that appears to be that we are now looking at the penalty that we're paying for adopting these fossil fuel energy sources. So here is a global temperature perspective here that you can see. We can look at the annual average, which is in these blue dots here. And you can see it goes up and down a little bit from year to year. And it's, we're not talking about massive changes from year to year, just a couple of tenths of a percentage point, but of degrees centigrade. But you can look at this long-term trend, and the long-term trend in CO2 is represented in this yellow line, in the green line, the atmospheric CO2. And then you can see that the CO2 that comes from combustion of fossil fuels actually really takes off after the 1950s, and it actually exceeds the atmospheric CO2. In other words, there's a lag time between when this carbon is actually produced in the atmosphere to the time where you actually see an impact in increasing CO2 percentage. And then you can see this red line, which is kind of an average of 5 years, but you can see that basically that's just all tracking as an increase. And in particular, the increase is somewhere, just took off somewhere after the 1960s, 1970s, somewhere in there. And there's simply, it looks like there's no turning back from any of that. So that brings us to what we can call climate forcing, which we'll get to in a minute. Well, here's a whole course for you. This is something that if I were to explain this in great detail, would take about a semester. In other words, we could look at all of the inputs, all of the exchanges that occurred here. And you can see that we have to start over here to the left. We have to talk about solar inputs. And those solar inputs are not constant. They change. And they have an effect on the overall dynamic because it's input versus output. You're going to look at this as your bank account. What you would like to have at the beginning and end of the year is a balance. You'd like to have a balance of the amount of energy that's coming in and the amount of energy that's going out, amount of money that's coming in, the amount of money that's going out. So you don't want a net gain, you don't want a net loss, you want a balance. So we have to understand how all of this is working and whether it's creating a balance or whether there's some imbalance in the system. So this is a really complicated figure. As I said, it would take a whole course to explain everything here, but you can see that you have every aspect of the surface of the planet is interacting with the atmosphere, it's interacting with the oceans. There are no separate parts anywhere here. Everything interacts with everything else. And you have the atmosphere, which is the atmospheric composition, which is really important because it has something to do with the amount of heat retained by these greenhouse gases, which we'll get to. And then you can see there's a volcano there, and you can talk about interactions with the biosphere. You can talk about soil biosphere interactions and so on and so forth. There are people all over the world still studying all of these interactions. And as I said, this is a whole course right here. But let's just take a look at this next one. It's a little bit simpler. And again, you can see these double arrows, arrow going in, arrow going out. And you can see that when we come to the ocean down here where I have my cursor over to the right, that you have vertical overturning in the ocean. That makes a difference. What we're seeing in the record now is that the heat that's been transferred from the atmosphere to the ocean is now going down as far as 1,000 feet into the ocean because of vertical transfer of energy. And you can see then we have to deal with ocean currents, temperature, salinity, and now we're talking about acidity as well, because acidity is affecting the ability of the organisms that form calcium carbonate to form that calcium carbonate. So we're worried about coral reefs and all those shell-forming organisms out there in the ocean because the acidity makes it less possible for them to actually produce the shells or the calcareous materials that they need. Anyway, I think you get the idea that there's interactions everywhere, and we can talk endlessly about those interactions. So again, this is another one semester course. And we could have a one semester course about the stratosphere, all of the things that we're talking about here. So here, we're blessed and we only exist because our planet has an envelope of atmosphere around it. Many planets have little or no atmosphere. So we have a thermosphere at the top. That thermosphere is somewhere around 53 to 375 miles above the planet. Then we have the mesosphere, sphere, which is 31 to 53 miles above the planet, and the stratosphere, which is, let's see, where am I? Mesosphere, stratosphere, which is about, I think, 10, I think troposphere is, wait a minute, I'm confusing myself here. I think the troposphere is 0 to 10 miles above the planet, and the stratosphere is 10 to 31 miles above the planet. This slide got kind of screwed up, so that's why I'm having to do this from memory. All right, let's see here. Again, this is a way of representing what happens in the atmosphere. You have incoming solar radiation is represented by this 342 here, and then you want to know what happens to all of those incident radiations that are coming in. You want to know how much is reflected by clouds, how much is reflected solar radiation, and so on and so forth. So you want to have some that's emitted by the atmosphere, emitted by clouds, and so on, and some that's absorbed by the surface, so on and so forth. So you need to understand this energy budget of all the stuff that's coming in. And then again, this is the sort of thing that people are arguing about and studying intensely in the atmospheric sciences. And again, this is another course. So let's go to CO2 for a moment, because that's the principal greenhouse gas that we're worried about, although there are others. You can see there that I've listed the other gases that we need to be concerned about. We need to be concerned about methane, nitrous oxide, fluorinated gases as well. But if you look at what's happening with CO2, and if we go back to 1850, there was CO2 was something like 250 parts per million. I don't remember the exact number, but look at it now. It's right now, November 30th, just the other day, I pulled this up, and it's 114.36 parts per million. And if you look at what happened 30th of November in 2019, you see that it was 10.7. So CO2 is going up. It's going up year after year. And my sense is that CO2 will probably reach somewhere around 500 parts per million, somewhat after January 2045 at the pace that this is all going. Just a little anecdote, I sat down with one of my colleagues who I stole some of these slides from, a man by the name of Fedema, who used to be a faculty member here at the University of Kansas. We sat down one day and tried to figure out the first month. This was a number of years ago. It was the first month in which the parts per million would be over 400 parts per million. And then we've also just sitting down having lunch and writing this down on an napkin. And then we figured out which month would be, and which every day would be over 400 parts per million. And we got them both right. I mean, this stuff is really relatively predictable. We know how much CO2 is emitted by fossil fuels. We know that there's a progression here. CO2 goes down in the summer months, but increases in the winter months. It goes down in the summer months because you've got all of the plant life out there in the northern hemisphere, which is kind of the dominant hemisphere in terms of interactions with CO2 by vegetation, pulling up a lot of CO2 out of the atmosphere. Because vegetation pulls CO2 out of the atmosphere, this is one of the reasons that people want to plant a lot of trees. Nobody is really sure whether that's going to have a sufficiently big impact, but it's obvious that vegetation is really important in this carbon cycle, and that we have to maintain a vegetated planet. There's no question about that. So this gets to what I was talking about just a minute ago, that possibly by January 2045, we'll have over 500 parts per million. I keep adjusting this figure, but it keeps coming back to somewhere in the mid-40s, the mid-2040s. We're going to be well over 500 parts per million at the present rate of CO2 input in the atmosphere. So one of the things that your friendly denier comes up with your climate denier comes with, is that CO2 has gone down and CO2 has come up over the years. In other words, you can go back in historical record. You can go to something called the Vostok Ice Core and the Law Dome Ice Core, and you can look at what CO2 was in the past by looking what was trapped in ice, and you can see that there have been changes over years. So in some parts of the past, we had as much as almost 300 parts per million CO2, but then it would go down to less than 200 parts per million, maybe close to 100, 180 parts per million. And you could see these cycles in the past, and people will say, oh, well, you know, if CO2 is going up, it's simply doing what it has done in the past. And that is just not so. If you look, oops, I keep doing this, I'm sorry. If you look over here to the right, and you see the what's going on here to the right, you see the current level, which is much higher now than it was when this graph was created. And this is a result of climate forcing. And climate forcing has to do with the input of CO2 and methane and fluorinated nitrous oxide and fluorinated compounds into the atmosphere. It has changed the pattern. What we should be experiencing right now, according to the climatologists, is we should be experiencing a slight decrease in temperature, but we're not. And the reason we're not is that we're forcing the climate. And the reason that climate is being forced is the increase in CO2. And the CO2, methane, nitrous oxide, fluorinated compounds are trapping energy. They're trapping outgoing energy. So if we look at how the energy system works, you've got a lot of incoming radiation. That radiation is reflected back into space, but it's reflected back into space at a much lower intensity, a much lower level than it is coming in. And that lower energy level is sufficient to be trapped in the lower atmosphere by CO2 and methane and so on and so forth. Methane, by the way, is it holds in re-radiated heat much more effectively than CO2 does, maybe at a rate of about 30 times, but CO2 is much more persistent in the atmosphere. Methane tends to be broken down a little bit more easily. All right, let's go on to the next. Now this gets to be a little bit harder to explain, but just bear with me a little bit. There was a man who was in prison. He was a very excellent physicist, and this occurred quite a while ago. His name was Milankovitch. And while sitting in prison trying to understand these patterns of alternative warm periods and cold periods, which would belong to glaciation or interglacial periods, this man by the name of Milankovitch, while sitting in prison, thought about how the Earth rotated. And it turns out that the Earth rotates around the sun, but it is not constant. It wobbles a bit. And as it wobbles, it turns a little bit more tilted toward the sun at some part of the long progression around the sun, and other times it turns away. So the direction that the Earth's spin axis is pointed toward the sun determines a lot about how much incident radiation hits the surface. And so these cycles affect the amount of sunlight and therefore energy that Earth absorbs from the sun. They provide a strong framework for understanding the long-term changes in the Earth's climate, including the beginning and the end of ice ages throughout Earth's history. Well, I don't know what I would think of if I was sitting in prison for months and months, but I'm sure it wouldn't be coming up with some solution to a magnificent problem like trying to figure out cool ice ages and warming periods. But Milankovitch did it, and hats off to him. His service to mankind here was significant and will be remembered forever. All right, if we talk about glaciation in the United States, you can see that the last glaciation dipped down here into northeast Kansas where I am. My neighbors right next to me, just a quarter of a mile away from me have a lot of glacial rocks on their property. I don't have any that I've found on my property, but these glaciers, as they move down, moved a lot of material from the northern latitudes down with the glaciers as it moved further south. And there are some interesting biological aspects to this that I'm not sure are totally true, but they are sufficiently myth-making. So I'll tell you about one of them. If you go to the south side of this thing in Kansas, it's just full of, there are chiggers everywhere. And chiggers, if you aren't from the Midwest, are just a real bane for most of us who live in this area. I mean, we've got to protect ourselves from chiggers and ticks and things of that sort. But if you go north where you have these glaciated soils, supposedly there aren't any chiggers. I don't know if that's true, but it doesn't really matter if it's true, is it? It makes a good story. Anyway, there's some other myths about the distribution of pheasants that are associated with this as well. But, you know, these are folk tales, and what we have to do is sort them out. All right, let's go on. Let's talk about the monarchs in the recent past and kind of get to the nitty-gritty here. And what I want to do first is take you to what's been happening out west, because out west really tells us a lot about not only what has happened recently, but it tells us what might be happening in the future. And this particular graph, and I'm going to have a lot of these, so get used to it, please. This deals with the June to August temperatures in Phoenix, Arizona, just as an example. And if you look over here to the right and see what had happened here in this past year, this past summer, oh my goodness, that temperature was beyond anything that we could possibly imagine. Can you imagine living in a place with temperatures where they were averaging as high as they were in Phoenix this past summer? And it just has taken off. I used to work in Arizona in the early 70s, the late 60s and early 70s, and I'm thankful that it wasn't as hot then as it has been in recent years. 116-degree days are not uncommon now in that part of the world. I think the highest we saw when we were doing research in Arizona was about 114, and that was only a couple of days, and oddball days in a couple of years. But now this is a common occurrence. All right. So if you remember what was up at the upper right on that figure, it showed that the temperature was increasing by 0.5 degree Fahrenheit per every decade in Phoenix. Well, it's even worse in Carson City, Nevada. The average temperature for June to August in Carson City, Nevada, which is just over the border from California and Nevada, is now going up by 0.8 degree per acre. I mean, that is just outrageous. That is an insane rate of temperature increase per decade. And I'll show you why as we go through more of these. All right, the next one shows you Savannah, Georgia, and looks what has happened to Savannah, Georgia. Now, you wouldn't expect that Savannah, Georgia would be heating up that fast, would you? But it is, and it's heating up that fast, as I will tell you and remind you again when we get to this, another figure, is that because of the ocean temperature. The ocean off of Savannah, Georgia, which is right on the Atlantic coast, is heating up. And the ocean temperatures, because oceans absorb about 90% of the excess energy that's held in by the carbon and carbon dioxide and methane and nitrous oxide, those greenhouse gases, holding all of that energy, about 90% of the excess energy is absorbed by the oceans. The ocean temperatures are increasing totally around the continent, and that's having a major impact on these coastal areas in terms of temperatures. All right, San Antonio, Texas is not bad. It doesn't look as bad, does it? This is the rate of increase for San Antonio. It's not as high as you can see for these others. It's only increasing about 0.2 degree per decade. At least that's what it looks like. Except if you look at the last couple of decades, it's probably doing even more than that. So let's go then to what is really happening in San Antonio. And on a long-term basis, and this comes out of a website for the city of San Antonio. The city of San Antonio is really looking ahead. They're trying to figure out where they're going to be and how they're going to have to adapt in the future to climate change. And so this nice little bar graph here, that's just a little histogram, shows us that in the 1890s, there were 3.9 days per year in which there were days with over 100-degree temperatures. But look at what's going on now. What's going on now is in the last decade, for which there are data in the 2010s, it's now 17.4 days a year in which, on average, on which the temperature is above 100 degrees. And if you project that forward, it's not hard to envision that by the time you get to 2040, you're talking about 40 or 50 days a year in which you're going to have over 100-degree temperatures. And that's what San Antonio is anticipating, and that's what they're trying to think about planning for. There's a tremendous increase here. Look what happened, 39 days in a decade versus 174 days in a decade. That's a fourfold increase, more than a fourfold increase. That's just incredible, all right? And a lot of organisms just can't deal with those really high temperatures, those 100-degree temperatures, and monarchs are one of them. All right, so let's talk about monarchs west of the divide here and kind of bringing this into context to try to understand what's happening to the Western population. Again, this is our subject, and this is what the people in California tell us about the populations. You can see that in '97, they seemed to think they had over a million butterflies. I'm a little skeptical about that, but looking at the climate data, but it's very, very clear that from the late 90s through really through 2017, they had a fairly robust population. They were talking about almost 200 million butterflies on average for each winter, and they weren't even looking at all of the overwintering sites at that time. So there were some down years and there were some better years, but you can see that the long-term averages were pretty consistent over a long period of time, with a little bit of perturbation because of probably some weather events. But now what? You get to 18 and it dropped down to about 30,000. You go to 19 and it dropped down to 30,000. So what is it going to be this year? This year it's going to be much lower. It's probably going to be around 5,000. That's just striking and it's just startling. All right, let's take a look at why that might be happening. Well, one of the things that we have to do is take a look at what's happened to the temperature in California. And if you do that, you see the long-term data says that it's only changing by 0.2 of a degree Fahrenheit from 1895 to 2020. But that's not the story. The real story is what's happened on a basis of 30-year records here. So if you go to 1901 to 1930, it was an average temperature during that period of 68.4. You add another 30 years, you're up to 69.4. You add another 30 years, you're up to 69.5. So you're not really increasing much for a 60-year period there. And then you go right up to 1991 to 2020, and you're up to 70.9. Holy smokes. Holy smokes, you've gone up 2.4 degrees in 120 years, 2.4 degrees. And if you look at that, 1.5 of that has actually, or 2.4 of that, this has actually occurred. I'm sorry. What is it? It's 1.5 of that has occurred. 1.4 of that, my math is not fast enough here. 1.4 of that has occurred in the last 30 years. In other words, about half of the change that has occurred in the last 70 years has occurred in the last 30 years. So that tells you a lot about what organisms are having to deal with in California to make those adjustments to these rapid climatic changes. And it's not just temperature that's involved here, it's drought as well. So as temperature goes up, you tend to have longer droughts, more frequent droughts, and so on and so forth. So those are things to keep in mind here and what's going on in California. So here, let's take a look at one of the other things that's happened in California. We have a lot of overwintering colonies in California along the coast, from San Diego, Santa Barbara, all along this coast, San Luis Obispo, Monterey, and Marin County up here, which is close to the northern limit of these overwintering monarch colonies along the California coast. So let's just see what has happened in the last few years with those colonies, the last few years named from 98 on. So I want to start here down at the bottom of this figure and go from 98. We have San Diego County, Orange County, LA County, 98. There were 39 different overwintering sites along the California coast in those three counties. And look what we had in 2018, only 11. And then if you go to San Diego County and you look again from 98, and then to go down to 2018, you went from 18 down to 3. And then if you look at Marin County, then you see that the pattern is a little bit different. In the Marin County, 98, 99, you had modest numbers of butterflies, but now things, only 5 colonies, but now you've got more colonies in the 15, 16, 17, and 18, and you've got more butterflies, and it turns out that that they now constitute a higher proportion of the total population, whereas Marin County only accounted for 2 to 3% of the population back in 1988 and 1999. Now it's closer to 9 or 10% or more of the population. So what's happened here? It appears to have gotten quite a bit hotter somewhere in the south, and that seems to be having an effect, and maybe that's what's going on. Let's take a look. All right, so the first figure here that you see is Marin County, and you're looking at the long-term average of 48.5 for the period of January to February, which is the main overwintering period in that along those coastal overwintering sites. But now look at the temperatures. The mean temperatures more recently are 50.2. Well, we can go down to Monterey County, and it started at 47.8. Now it's 49.8. Historically, it was 48.3 in Santa Barbara County. Now it's 50.2. And look what's happened in San Diego. San Diego, it used to be 50.4. Now it's 52.8. And why has that occurred? Why is it getting warmer along the California coast? Well, I don't have the figures to actually show you, but what's really happening is that the ocean is warming up along the California coast. And the warming ocean, there's usually a cold current that runs down the California coast from the north, coming off of Alaska. It's coming down across along British Columbia, then Washington, and further down. But as you look at the temperatures as they approach, say, the San Diego area, those temperatures are now, just looking at them the other day, they're now in the 60s. And because they're in the 60s, the adjoining land masses in the winter months are really heating up, and they're heating up in a way that is having a negative impact on overwintering of monarch butterflies on the California coast. So here is kind of a summary of all of that. The mean temperatures along the California coast have increased by an average of about 2 degrees Fahrenheit since the year 2000. Numbers of overwintering sites and monarchs are declining in Southern California counties. Northern California counties are now contain higher proportions of the total overwintering monarchs. Temperature increases during fall and winter over the next 20 years will impact the number and distribution of overwintering sites. I don't think there's any doubt about that. Higher breeding season temperatures and droughts will have a negative impact on population growth. It's already happened, and it's going to happen again. I mean, this is what really happened this summer. We had very high breeding temperatures in the west, and there was a significant drought, as you know, and then a lot of fires. It's really tough for the butterflies to deal with all of that. Increasing number of days of 100 degrees Fahrenheit will reduce the monarch breeding range, and there's already a nice paper talking about this with respect to Idaho and Washington and Oregon. Those temperatures are going up in those lowland areas in those states, and it's going to reduce the capacity of the population to produce during the summer. This past year, there was virtually no monarch production in the Northwest. That's really one of the big reasons that there are very few butterflies at these overwintering sites this winter. Okay, conclusions based on the Thanksgiving counts. Population increases are associated with temperatures close to the long-term averages. Population decreases are associated with higher than average temperatures. Negative factors include a lot of things to do with temperature and precipitation. I'm going to skip over the details there, but this has to do with a detailed analysis I've done. Total population sizes ranging from 205,000 to 235,000 from 2001 to 2016 suggests to me that habitat loss was not the major driver, as some people have talked about, of monarch numbers over the last 20 years in the West. I think it has to do with temperature. Future droughts and high temperatures will limit population growth in the Northwest, as I said, and contributions to overwintering colonies from the Northwest and really the East. I'm talking, that should have been the East there. I'm talking about Nevada and so on. That's likely to vary substantially from year to year and probably going to decrease. I've got a stage-specific model I don't have time to talk about, but predicts the direction of the population change 13 out of 18 years, but it doesn't predict the amplitude. In other words, I already have a model that predicts what is going to happen to the population given certain physical conditions, and the model has been right 13 out of 18 years. So it needs some refinement. I need to be up there, say 16 out of 18, but I think with a little bit more in the range of data, a little bit more data that speaks to the positive and negative effects, I'll have that worked out. All right, monarchs east of the divide, let's go to that and try to understand what's going on. But here is the kind of piece de resistance, if you will, about what is happening globally in terms of the United States anyway. And this is not too different from what's happening elsewhere in the world. As I mentioned earlier, what's happening along the coastlines is that the ocean temperatures are heating up along the coastlines. So we're seeing a higher temperature in the Pacific that is influencing the patterns of climate in the West. And we're seeing warmer temperatures along the East Coast as well. But this particular graphic represents the rate of temperature increase on the basis of it per decade from 1975 to 2020. And you can see all of those red states. This is not a political thing. A lot of those states are blue otherwise. But a lot of those states pictured in red have just outrageous rates of temperature increase, and they're mostly in the West. But you can see that all of the coastal states, including Texas and the Gulf Coast states and the coastal states along the Atlantic coast, all of them have relatively high temperatures except Maine. And then you see that the rate of change in the Midwest is much, much lower. And that's a good thing for monarchs and pollinators and so on and so forth. So we want to see that rate of change. But why is the rate of change so much less in the Midwest? The answer appears to be the presence of a jet stream in the summer, which lies just above the Dakotas and Minnesota. If that jet stream dips down as it has in 2004 and 2009, then the temperature drops in that central region of the country during the summer months, and we can see that monarch populations drop as well. In other words, the cooler temperatures, they can't produce as many butterflies. The population declined in both of the years in which the jet stream took a dip down the Midwest. Now, the real fear about the jet stream is it is not going to stay above the Canadian border. But we're seeing patterns of atmospheric change around the planet. Some of the patterns of wind distribution and moisture distribution on the basis of wind, long-term wind patterns are changing. In other words, we're modifying the climate by modifying the landscape in various ways. The decrease in the forests in the Amazon is changing the amount of moisture that reaches the clouds, and the clouds that would normally be dispersing southward in South America to the southern countries in South America those clouds have less moisture, they're creating droughts further south and major fires further south. Not only that, but there's a lot of fires in the Amazon as well. So we've got major changes to worry about if that jet stream goes further north than it is right now, or it has been over the last 40 years or so. Then those areas in the Midwest are going to heat up. But I have no way of predicting what the jet stream is going to do. But in any case, what this does is it tells us something about the resistance to kind of understanding climate change, doesn't it? If you look at the green and yellow states, where climates are not changing really very fast, people just are very resistant to the idea that the climates are changing. On the other hand, it's very clear when you go to the east and west coast, and even the Gulf Coast states, that climates are changing pretty fast. So we're not all of the same mind of what's happening, partly because we have different experiences in this country based on what we can see just looking out our window, or what our experience with nature is. So that's part of the message here, but the message also is that we really have to be concerned, because this is not a static map. This map is telling us not only what has happened in the past, but it's telling us what is likely to be happening in the future. Another 2 decades of high temperatures in those red states, and things are really going to change, So you're going to see a greater discrepancy between the coastlines and the Midwest than you actually see right now, because the Midwest is actually increasing probably only at up to 1/7 the rate, 1/6 the rate, 1/5 the rate that the coastlines are changing. So that's a concern. All right, I've spent too much time on that. Again, tagging monarchs, or overwintering monarchs, what's their fate? We know that the populations have been going down, and what we also know is that the major reason for the population's declines have had to do with the loss of habitat. And we could go into great detail about that. I have on many occasions talked about habitat loss as being a main driver of what's going on with monarchs, but we have to also consider what's going on with climate and with weather events, and whether that is having some sort of impact on the butterflies or any other pollinators for that matter in the Midwest. So right now our population is mostly centered north of 40 North, which is, say, St. Joseph, Missouri, and north of that at those latitudes above, because that's where most of the monarchs are produced that reach Mexico. And we also have to be aware of the fact that most of the monarchs reaching Mexico originate from just west of Madison, Wisconsin, to the center of the Dakotas. And so we have a relatively centralized population. We have a lot of butterflies that are produced in the northeast, east of Madison, Wisconsin, but relatively few of those make it to the overwintering sites. So we really have to focus on what's happening in that main corridor for monarch butterflies. And what we can see here is average temperatures for March in Texas have been increasing, but it doesn't look like really bad, does it? But if we dissect what's happened in the last 25 years or so, we might get a different picture. So let's get to that. If we look at precipitation, we can see that, yeah, there have been some years with precipitation particularly low, like 2011 in Texas. But if you look at droughts in Texas, they were much more frequent in the past than they have been in recent years. So let's take a look at temperatures for the first and second half of the period that we have good monarch data. So we have good monarch overwintering data from 1994 to 2018. And then what I've got here is I've got years, I've got Texas, MR means March. I've got the Midwest, I've got MY, which means May. I've got Midwest, which means, and then I've got June through August, Midwest, August through September, and then Texas plus Oklahoma, and that's September and October. So if we look at all of these, these two periods, 1994 to 2005, we see we get 81, but if we compare it to what's happened from 2006 to 2018, there's been a tremendous jump. Texas March temperatures are going way up. Oh boy, that doesn't look good. If we go to May, temperatures are going up, but not as much, and they're going up across the board here. But what's really alarming to me is what's happening in March, because what happens in March determines a lot about what happens to the population for the entire year, whether the population has a good year or doesn't have a good year. And the reason that March temperatures are really very impactful for monarch butterflies is that if the temperatures are too warm, they send the butterflies too far north too soon. And if they get too far north too soon, they are laying eggs in environments which are colder, takes their progeny longer to develop. They lose a lot of progeny due to frosts and things of that sort. And the population just doesn't grow as well. So you want to keep your babies in Texas. That's the model here that we want to talk about. We need Willie Nelson to sing a song like that. All right. So if we look at Texas March temperatures, if we look at any temperatures with a greater than 1.9 Fahrenheit above average in 11 out of 19 years since 2000, the mean was 2.6 Fahrenheit. If we look at the 1.9 Fahrenheit above average from back to the beginning of our temperature records, which was 1895 to 2000, it was only 25 years out of 108 years versus 11 out of 19. So the projected mean for March in Texas is in the 2040 to 2050 period is 6.0 Fahrenheit above the long-term average, which is not good. But we have seen spring averages like that in recent years. Monarch numbers have declined in 9 out of 11 years with temperatures above 1.9 Fahrenheit. And monarch numbers have increased in 4 out of 4 years with temperatures below 1.5 above normal. So March temperatures are pretty critical. That's pretty obvious. We still have some details to work out about how that works, but clearly this is the vulnerability that we see most significant in the Midwest. Summer temperatures tend to be much more stable, but they, as I showed you from the Midwest, Texas is increasing in temperatures faster than the Midwest is, and that's what the concern is. And a lot of that temperature increase is actually occurring in the spring months rather than in midsummer. All right, monarchs in the near future, and this is where we all need to be concerned. If we look at Oklahoma temperatures, a lot of you are from Oklahoma. Let's take a look at that. Oklahoma doesn't look bad, does it? Oklahoma looks pretty good. If going from decade to decade, they got about a 0 rate of change from April to October, which should be your growing season. So, you know, that looks pretty good, but it's right in the center of the continent. You're doing well, but will it last? That's the question. In terms of moisture, you're getting a little bit more moisture per decade over the years. You've got you've got droughts to deal with in Oklahoma, but you have fewer droughts now than you've had in the past. But here's the reality. In the 1950s, this particular graphic shows you the average springtime temperature, and you can see that it is going to get a lot warmer by the time we get to the 2090s. These warm temperatures where we're getting excessive heat is really going to increase. I wish I had a better graph for this, but you can see that it's going to get warmer and warmer because of these Gulf temperatures. The heating of the Gulf Coast is going to be pretty dramatic in the future. So this is a little bit better. I wish this was a larger slide, larger picture here, but this gives you an idea of what the recent past has been in terms of the number of days which will have 100 degrees Fahrenheit. And you can see that we get a number of days with 100 degrees Fahrenheit that occur mostly in Texas, Oklahoma, a little bit of Kansas. But as you get, that's the recent past, but as you get into low emission scenario of 2080 to 2099, you can see that the number of days where we're going to have 100-degree temperatures actually increases, moves up the Middle West, and that's pretty dramatic. So the Midwest is going to change. That's very clear. And if you look at what's going to happen in the 1890s or 2080s to 2099, and you look at a high emission scenario, which is quite possible, you're going to have 100-degree temperatures all the way up into northern Minnesota. That's just outrageous. So, and what this pictures is that if you go out here to the west isn't going to heat up as much as the Midwest does, if this scenario is correct. So these are things to be concerned about in the future, and we do need to worry about those days above 100 degrees, because that's going to drive a lot of the engines here economically. It's going to drive agriculture. It's going to drive how we live. It's going to make me wonder whether we're going to be living underground pretty soon. All right. We want to keep these butterflies flying. This is one of our magical things that we have to do within this planet. We have one of these magnificent migrations. This is the only insect migration that of this size and scope, which is a two-way migration. And it is the most spectacular insect migration on the planet by far. And it connects a lot of us with what's going on in nature, and we need to maintain those connections. So we need to maintain habitats for monarch butterflies going into the future. And we need to tell our politicians, our neighbors, and everybody else that we can influence that if we value pollinators and monarch butterflies, we have to invest in their conservation. And as part of that process, we need to convince the world to reduce greenhouse gas emissions. All right. Well, thank you very much. Appreciated having an opportunity to talk to you, and I hope I didn't keep you too long. But I see that I have.
No, you haven't. So we have a few questions now, if you're ready for that.
I am ready.
Okay, so the first question is, what is the half-life of CO2 in the atmosphere?
Ooh, I should have looked that up, shouldn't I? I think it's about 30 years, but I'm not absolutely certain.
Okay, so well, we can do further research on this. I think that's something I'll have.
Yeah, I think you can look that up. I mean, I do a lot of Google searches on these things, and that's one that has not stuck in my mind, but I think it's about 30 years. It's about a 30-year lag time before. This is one of the things that concerns everybody, is how many lag times there are in the system. And lag times mean that, you know, you have an input, but you don't feel the result of that input until some later time. So one of the things that happens that I didn't really point out is that CO2 increases and temperature follows. So the question is, how much does temperature lag CO2 input? And the statements usually are around 30 years.
Okay. All right. Next question. Are we in uncharted territory for the current levels of CO2 and temperature increase?
Yeah, we are. I mean, we haven't had anything like this for how many millions of years? I had a figure there that I think I glanced over, that we're talking about millions and millions of years since we've seen CO2 this high.
Okay.
That thing was on there, but I forgot to emphasize it. I mean, we have to go back something like 5 million years before we have CO2 at this particular level. And at that, I don't know what happened to that slide. I must have skipped over it. But at 5 million years ago, sea level was 50 feet higher than it is now. And we had forests that were all the way up to the Arctic. It was much, much warmer as a result of those high CO2 levels that we have now. But, you know, so potentially if we stayed at this particular CO2 level, we could go back 5 million years. I don't want to do that.
Okay. Next question. Okay, this is an easy one. Will this recording be posted to the TAP website? And the answer is yes. All of our webinars are posted to our website, and please feel free to share them with everybody because we'd like to get this information out as much as possible. Next question from our friend Dr. Richard Grounds over at UT Language Project. On my last trip to Haskell Indian Nations University, I was reminded about a recent NPR story about dramatic absence of songbirds across Kansas. Is that loss connected to reduction of insects due to temperature rise, and could you comment on interconnections across different strata of animal and plant life?
Yeah, there's a lot of concern about what's going on with birds. There was a report a year, when was it? It was in the fall of 19, which talked about we have lost something like 50 million birds. And I'm doing this from memory, so you could look this up. And one of the big losses has been losing grassland birds. I think there's something over 20 species of grassland birds that have been declining significantly. And the reason for that has to do with the decline in grasslands. We have not done a good job of maintaining grasslands. So a lot of the big decreases have involved that. In fact, I've written about this, and it's published several different places. I think you can find this on our blog about the loss of birds. But as far as songbirds are concerned, that's a little bit harder for me to figure out. I think the best way to get the answers for that question would be to go to the Cornell website, which talks about all the bird surveys that are being done, and they could give you some up-to-date data on that. Yes, insects decline is a concern, and that is a concern relative to most of the songbirds that are insect dependent. There was a notable decline in insects across much of the eastern United States this year. I've received many emails about this. People are much more aware of this now. I noticed a lot of declines on my property of insects that used to be quite a bit more abundant in the past. I don't know whether this is temporary or whether this is long-term. If it's long-term, it does not speak well for what's going to happen to birds. That doesn't speak well for what will happen to birds of prey. That doesn't speak well for what will happen to a lot of other things. You know, the system out there is highly dependent upon the interactions between and the interdependence between plants and their pollinators. And if the insect pollinators really go down, that means plant diversity is going to go down. And you know, you have so many organisms out there that are dependent on the fruits, nuts, berries, you know, roots, shoots, and leaves, and foliage, and stems, everything out there. That if you lose a lot of plant diversity, you're going to be losing a lot of other diversity as well. So maintaining those pollinators is extremely important, and this is what all of our activities are designed to do. You know, by protecting monarch butterflies, we're protecting all those pollinators, and that includes protecting ground nesting birds and so on and so forth. So it's keeping the system together. It's maintaining all the connectivity out there that's really fundamentally important in this mission that we all should be engaged in.
Okay, and we had a quick comment here from Ray Morans, who said, according to the web, chip is right about the 30-year half-life of CO2. Next question from our friend David Carell at Chickasaw Nation. Will the monarchs and insects adapt to climate change?
Yeah, the question is, you know, what sort of adaptations can things make to climate change? And the standard answer is that we don't know, but there will be winners and there will be losers. And we don't know who the winners and losers are going to be because we don't know how adaptable and flexible a lot of things are. What I'm seeing in monarchs is that they have a lot of capability, but they have their limits. And whether they can adapt and evolve fast enough to deal with the pace of change is really the question. And the pace of change is probably a lot faster than evolution and adaptability can accommodate for a lot of species.
Okay, and which follows another question we received is, if nothing is done, how long will we have monarchs?
It's hard for me to imagine that we're going to have monarchs the monarch migration by 2040 or 2050, somewhere in there. You know, if we don't do something about CO2, if CO2 is not reduced, if we're, you know, simply going along at the same pace we are now, I have a hard time seeing that we're going to have monarchs in another 20, 25 years. And there are several reasons for that. One is the increasing temperatures in Texas in March. Another one would be anything that would happen to increase the number of 100-degree days in the Midwest. And beyond that, then you have the warming in Mexico that would effectively push these overwintering monarchs off the top of the mountain. It would just simply be too warm, just as it's getting too warm along the California coast.
Okay, and then one more question. Will ocean warming and acidification affect CO2 absorption?
Yes. Well, CO2 is being absorbed in the ocean, and it's making the ocean a lot more acidic. And the ability of CO2 to be absorbed into the ocean is partly a function of temperature, and the temperature is increasing in the oceans. So I'm not sure I've answered that question correctly, but that's the way I see it. I see CO2 has already made the oceans a little bit more acidic. That's going to have a major impact on all of the inshore fisheries around the world. We got 1 billion people around the planet that are dependent upon inshore fisheries, which means these are coastal fisheries that are highly dependent upon coral reefs and other sources of structure that allow fishes to be diverse and abundant close to shore. As those resources decline due to acidification, then you've got a lot of people that are not going to be able to feed themselves based on those inshore fisheries. So there are a lot of different things to think about here.
Okay. And our next question from Bree Dunham, our dear friend over at the Citizen Potawatomi Eagle Aviary. Can regenerative agricultural practices really help? If so, should we be pushing for more regenerative agricultural practices, making it almost mandatory?
Well, making anything mandatory is probably not something that we can easily do or want to do. People bristle even by wearing masks these days, and it's crazy. But everything that we can do that sequesters carbon, everything that we can do that minimizes carbon input into the atmosphere is really beneficial. And a lot of the agricultural practices that could sequester carbon could be improved. There's no doubt about that. So yes, we should do what we can. Mandating it is probably not what I would choose to do, but certainly recommending it and show that it has economic and social benefits. Yeah, that's where I'd go.
Okay. Next question. Are temperatures in Mexico increasing as fast as the U.S.?
I don't know. I haven't looked at the temperature data in Mexico in general. There are people who are doing that and modeled what's happening in Mexico, have modeled what's going to happen in the area of the monarch overwintering sites. And their data is suggesting pretty much the scenario that I told you about earlier, where we've got maybe 20 years, 25, 30 years before monarchs will be pushed off those mountains.
Okay. And one more question. Are other species of butterflies as vulnerable as monarchs to the temperature rise?
Yes, and several species, many species perhaps, are even more vulnerable to monarchs than monarchs are. Monarchs are probably one of the more resistant species to a lot of climate change things because of their ability to migrate and connect with a lot of different habitats. What we can see with a lot of species, and there are various people doing research in the West, that a lot of species are declining really fast, faster than monarchs are. And that's because they are highly dependent on single plant sources, highly dependent on nectar. And there's a nectar connection with a lot of bees as well. So as temperatures go up to a certain point, and as soil moisture goes down, nectar production goes down. And that has a striking impact on species that are nectar dependent. I mean, I was talking about bumblebees earlier. Bumblebees are highly dependent on building nests and producing reproductives. Any sort of nectar or pollen shortage during the growing season has a tremendous impact on the size of bumblebee colonies and their ability at the end of the season to produce reproductives that survive the winter. And so this goes across the board. You got to have resources, and a lot of species are resource short when it comes to having high temperatures and low moisture.
Okay. Well, I think that is all the questions. If anybody has one more question, we still have time. Type it in. Otherwise, thank you so much, Chip. That was really, it was both fascinating and kind of frightening, kind of terrifying, but it was very, very well done in terms of making that science accessible to all of us who are not climatologists and scientists. So thank you for that.
Well, I'm glad to help, and I'm glad to hear from many of you, and I know a whole lot of you that registered, and thanks for attending. Appreciate it.
Hey, Chip, did you want to talk about windy.com real quick before we leave? Did you want to mention that?
Yeah, let me do that. So there's a website, folks.
Good.
Am I still sharing my screen with you?
Yep, we can. Yep, we're still looking at it.
All right. So I've shown this website to a number of people. It's called windy.com, and this website is pretty fantastic. So let's go to the United States. You can get information on the climate, the weather patterns. I shouldn't say climate. Climate really refers to a 30-year period. Weather patterns are what we deal with on a day-to-day basis. Let's go over here to the right and click on temperature. And this shows you the current temperature map for the United States. And you can see that cold weather has been coming out of the northwest. It's moving progressively into Kansas, then into Oklahoma, in the western part of Oklahoma. And then you can see, if we just do one click, there we go. I can tell you that right here in the center of Missouri, it's 28 degrees Fahrenheit. Now let's go in a little bit. So a lot of you live in Oklahoma, and let's go to Tulsa, and I'll show you what the temperature is in Tulsa right now. And it says 40 degrees. Now, if you go to your iPhones and look at what the temperature is supposed to be in Tulsa, your iPhone's going to tell you it's 39, 40, or 41. Probably going to tell you that it's 40 degrees Fahrenheit. Now, here's the other thing that's really pretty cool about this site. We're looking at present temperatures. Let's go down here and look at what's going to happen tomorrow. And tomorrow at 1 p.m., it's going to be 47 in Tulsa. And if we go over to Saturday and we go to 2 p.m., it's going to be 55. And then we can go further. It's 11 a.m., it's 49 on the 6th. And on the 7th at 11 a.m., it's going to be 39. It's going to get a little colder, Tulsa. And then it's going to be 51 again. So you can go, you got a 9-day record here that you can go in the future. And what you can see is all these little arrows around here, and so you can see whether you're going to get, you can see what your wind is doing. So if we switch over to wind, you can see wind patterns, and you can go through this wind on a day-to-day basis. Now the wind is coming out of the southeast, whereas previously it was coming out of the northwest, or no, it was coming out of the southwest. Now it's coming out of the southeast. And so you can see what the wind is going to do. You can get an idea of the velocity of the wind. You can look at air quality. You can look at clouds. Let's look at rain and thunder. Let's zoom out, and we can look at rain that is going to occur, rain and snow. So this is snow over here, and the temperature that tells us we're going to get 9/10 of an inch of snow up in the mountains in Idaho. So I would suggest that if you really are interested in what is happening on the planet and you want to understand what's going on climate-wise, that you get on this particular site and play with it. There are lots of layers. You can look at surface layers here. You can go higher. You can increase in elevation. You can look at thunderstorms, and there aren't any thunderstorms within the U.S. One of the fascinating things about this is looking at all of these hurricanes that have come out of here. Let's go back to temperature. One of the things that's happened is that there has this area in the Eastern Atlantic used to be, this is where most of the hurricanes originate, just off the coast of Africa. By the way, a lot of dust comes off the coast of Africa, gets all the way to the United States, comes across, because you have this circulation that goes from east to west at these mid latitudes. You can see that right now. But earlier, about a month ago, this area was really striking. Here I'm hit the temperature in Venezuela, it says 86, but that was the temperature you used to see over here. All that energy that builds up in the warmer parts of the year has to run downhill. That's going from high energy to lower energy states. And that means that you have these hurricanes that come out of this part of the world and they sweep across the Atlantic. And if we're lucky, they actually make a turn, come up the Atlantic coast and don't even get to the United States. But what we've been seeing recently is that a lot of these hurricanes have been coming across the Atlantic, have been stayed at this mid latitude, and then they've been coming up the East Coast, or we've seen a lot of this energy in the Gulf area and the Caribbean. We've seen that these temperatures, they're low now, 73 now, but a month ago, those temperatures were 80, 81, 82, 83, and that resulted in all of those hurricanes that came ashore in Louisiana that we heard about. So you can look at these temperatures. You can also look at, see, I didn't have the slide showing the currents, did I? So one of the interesting things about the global circulation patterns is that there are waves and currents, so that as you come down the East Coast, as you come down the, you come down the West Coast of the U.S., you've got a current that comes down south. So you got a current that just kind of moves down. This is illustrating what I was talking about before, these higher temperatures off the coast. See, that's higher than the average overwintering site temperature by a big margin. Those temperatures off the California coastal used to be a lot cooler than this. And they're much warmer now than the butterflies can tolerate from the immediate coast. And those colonies in the west are right on the coastline. They're virtually within a mile or two of the coastline. So they're strongly influenced by those oceanic temperatures. Anyway, I don't want to belabor this, but I would suggest that you get on this site and play with it. I've shown this site to a number of pilots. They get very excited about it. They haven't seen anything quite this good, because if you want to find out what's going on in Japan, because you're going to fly there, or someplace in the Philippines, or you're going to go to Thailand, you got a hurricane or a cyclone that's coming ashore there, you can understand that. You're flying to India, you want to know what's going to happen in Mumbai. You can get really a pretty good indication of what's going on in Mumbai. You're going to Sri Lanka. You know, any place in the world, you can get travel information, you can get weather information, you can understand what you got to pack in your bag, and so on and so forth. So yeah, it's a pretty extraordinary site. I haven't told you all the things you can do with it, but you can do an awful lot with this site. And I consult this site at least once a week to get an idea of what's going to happen on a large scale over the next 10 days or so. One of the things that you can do is, let's go back to the United States. Go back to the United States. One thing that you can do is zero in on, let's go in on Tulsa again. And we go in on Tulsa, and we can pull up, how's it go? Here it goes. You can pull up a detailed hour by hour temperature change and cloud change. Look at what you got all across the bottom there. You've got clouds, you've got temperature, you got moisture, you got wind velocity, wind direction, and so on and so forth. That's pretty extraordinary. So you can plan your picnic on the basis of that. All right. Well, I think that's all I need to introduce you to that site. I'm happy to answer any other questions you might have.
Okay, then there was one other question from Bree. We're trying to focus on several different nectar plants that bloom at different times of the year. Anything specific we should think about?
Well, I would think about your fall plants and your spring plants, in particular for Oklahoma. You need nectar sources for the butterflies coming north. You need really good nectar sources for the butterflies coming south. One of the things that all of our data on tagging shows is that tagging success and getting to Mexico is a function of greenness, which means that the greener things are, the more nectar there's going to be. So you can't control the amount of rainfall, but you can make a contribution if you maintain as many fall nectar plants as you possibly can, so that if you do have the right soil moisture, monarchs will be able to access the nectar.
Okay. And one other comment from Bree, which is a great comment. She says that we also use this site, the Windy site, looking at GPS tagged raptors and comparing to their migrating patterns. It's pretty cool watching Goldens ride storm fronts. Okay, that's pretty cool to think about, I think. So thank you, Bree. Okay, and so just one more, again, reminder, please go to our new website and register for the next webinar. We'll have information there on the upcoming conference soon, and we will also have this webinar recorded and posted there as well, that you can share the link with others. We have a new sign up on that website for if you want to officially join Tribal Alliance for Pollinators, and then you get all of our emails and all that kind of stuff. And one other thing about the new website is that we have our seed bank online now, so you can see all the different inventory, the different plants we have in there, and we also have our lending library of tools and equipment on there as well. So all sorts of good stuff, and we'll be continuing to add content to that website, but it looks amazing now, and Colin Spriggs worked really hard on that, so he did a great job, and it looks fantastic. So thank you all so much for joining us today. And and one more quote here from Carol Clark for Bree. Ray Morans has produced a nice nectar plant list for Oklahoma. So all right, so thank you all. Thank you, Chip. Amazing presentation, and we'll see you all later. Hito hey. Thanks. Bye-bye.
Bye-bye, everybody.